everybody, Max Glover here, Applications Engineer Extraordinaire for Intel. I want to take a few minutes and talk to you about a real-life fairy tale. We'll call it The Chip That Almost Wasn't. Now, most of you think of Intel as a product development company, which we are, but there are some unsung heroes within Intel, the technology and manufacturing group. Their job is to take our designs and make them a reality, and then make them commercially viable. Here's Fab 32 in Arizona. This represents a $3 billion investment to Intel, so it's safe to say that when these guys and gals commit to something, they better know what they're doing. This is Gordon Moore. Not only is he the co-founder of Intel, he's also the author of Moore's Law. Essentially, Moore's Law states that every 24 months or so, the number of transistors on a chip doubles. That is the catalyst for the performance increase in computing that we've been enjoying over the last 30-some-odd years. However, the Technology Manufacturing Group determined a few years ago that the move from 65 nanometer manufacturing to 45 nanometer manufacturing may not allow us to keep up with Moore's Law. To understand this problem and the consequences, we have to look at the basic building block of a processor, which is a transistor. Its function in life is incredibly simple. It's going to represent a binary 1 or a logical 0. That's the building block of all computing, and when put with 800 million of its friends, like in today's quad-core processors, can do some pretty complex things. Now, in the case of an NMOS transistor, when this transistor has voltage applied to the gate, the electric field that is created draws all these electrons into this channel. When that happens, current is able to flow across the transistor and the transistor turns on. That's the logical 1. However, there is a small piece of material here, the insulator, which is supposed to keep all those electrons intact and in that well. If that insulator breaks down, well, you have electrons shooting out every which way. That's leakage current. Now, the manufacturing guys thought that when we went to 45 nanometer, that's exactly what was going to happen because the insulator got too thin. Okay, so we lose a few electrons. What's the big deal? Well, when you take it again, in scale, 800 million of these guys, you're going to have some ugly issues. You have heat. Now, heat is expelled from a system, whether it's a laptop, a desktop, or a server. And not only is that uncomfortable, but, of course, the things that we use to control heat, fans, those will kick up, and that just adds to the discomfort. Also, since you lose all this power that you're paying for out of the wall, your electricity and efficiency there is not going to be up to snuff. This is only going to get worse at 45 nanometers unless there's a change. Let's liken it to me breaking into your house in the middle of the night, going into your garage and poking a hole in your gas tank. You'll get up the next morning, you'll drive around, but your efficiency is going to go way down the tubes because everywhere you go, you're just dropping gas out that hole in your gas tank. Gas mileage goes down, efficiency goes down, you don't get what you're paying for at the pump. Big problem. That's the same thing we're talking about on the processor scale of things. Now, back to the transistor. This insulator is the big problem because in 45 nanometer process technology, it's only 5 or 6 atoms wide. So that doesn't give us a whole lot of material to work with to keep these electrons intact. So our manufacturing R&D guys went back to the drawing board. They said, well, we need to find a different material that will work as an insulator on this new process technology. They went to a deep, dark corner of the periodic table and found an underappreciated and relatively unknown element, hafnium. What's nice about hafnium is that it's physically very thin, but electrically very thick. This is a great departure from the silicon and silicon oxide combination that we've been using since the 60s, and it was certainly unproven. The manufacturing guys made a big bet and decided to research hafnium 3-4 years ago. So it was a long road and there was a lot of hiccups. What happens if they fail? Well, Moore's Law wouldn't keep rolling, and we're going to have a stagnation in innovation. I know it's a scary thought, but it's a lot riding on this manufacturing transition. Really, it's the whole future of computing. If we can't move forward, then we're going to stagnate and we have no innovation. Luckily, in 2007, they were successful in making this product commercially viable. Here the 45 nanometer processors rolled off the line, and as of November 2007, they are available to you and I. First, we've released the 5400 Xeon processors. Beautiful thing about 45 nanometer. Of course, with Moore's Law intact, we have more transistors to play with. Biggest increase you're going to see, well, we've doubled the cache size. So on a quad-core processor, we got 12 megs of cache. Dual-core processor, we have 6 megs of cache. Good stuff. Also, because we made the transistors smaller, we're able to switch them faster, which means that clock frequencies can improve. So you're going to see many clock frequencies above the 3 gigahertz mark. Also, power consumption, especially under load, is going to get very much better because we've stopped some of that leakage current. So when this thing's going at 100%, whether it's a laptop, a notebook, or a desktop, you're going to see improvements in power consumption there. 5400 series is out today as of November 2007, but we haven't forgotten about the desktop enthusiasts. We also have the Extreme Edition QX9650. Just a phenomenal processor, and as Tom Hardware says, less noise, more efficiency, more speed, and more overclocking potential. In short, it's the best desktop processor anybody's ever seen, and it's available today. Now, 45 nanometer is only going to get better, and we're going to release our mainstream desktop and mobile processors early in 2008. So you'll see Core 2 Duo and Core 2 Quad, 8000, 9000 series, and we're going to switch many of our manufacturing plants over to 45 nanometer production. That's great news for you, that's great news for me, and luckily the manufacturing guys were able to tough it out, and we're going to keep innovation rolling. So until next time, I'll see you later. Thanks.